think of all of the solving that you've done to this point. You've done some really nice linear things. You've done some quadratic things. You did some logarithmic things, exponential things. Well, what's the next step? Of course, trigonometric equations, solving something that has a sine, cosine, or tangent in it. Yippee skippy. But honestly, it is really no different than what you already know. Let me show you this. Look at this algebraic expression here. You know how to solve something like this. This is 2x plus 1 equals to 0. You would bring the 1 over to the other side, right? Divide by 2, giving you x equals 2 minus a half. Yippee skippy, right? Well, guess what? Trigonometric functions are no different. They really aren't. They're just going to involve one extra step, and that's that sine part right there. So how would I go about solving this? Well, simple. I would go 2 sine x plus 1 equals to 0, exactly like the algebraic one here, right? Bring that over, divide by 2, and I would get sine x equals to minus a half. But the thing is remember, this is a trigonometric value. So, yep, I'm going to have to bring in that wonderful thing, and I'm going to have to find out where sine is negative a half. Well, we'll do that eventually. But can I do this graphically as well? Well, of course we can do this graphically. If we can do something algebraically, we can also do things graphically. Pull out our nice little graphing calculator, and bada bing, bada bang, get a beautiful value. Right? Now, let me show you how to do this, because graphically it's kind of interesting to see what's going to go and what's going to happen here. Let's look at this equation again. One last time. Look at this. We have 2 sine x plus 1 equals to 0. Soon as I see this idea of equaling to 0, that reminds me of something. Do you remember when we were doing things like parabolas and we let something equal to 0? Yeah, we're going to find these guys. That's right. We're going to find the zeros, right? We're going to find the intercepts, specifically the x-intercepts. We're going to find the solutions, right? Right? Roots was another word that we used, all indicating the exact same thing, these points. Well, how is this any different? Well, it's not. Let me show you what this looks like on your graphing calculator. It's actually quite hilarious. So bring up the old graphing calculator, and I put it in there for you already. So 2 sine x plus 1. Now, here's a neat thing. What about those window values? Well, the neat thing about the window values is this. If you go over to Zoom here, look what this says way, way down here on number 7. It will set up your window values to the best ability of trigonometry. What do you mean? What do I mean by that? Guess what? It's going to take all of the stuff that's trig important and set up your graph so it looks really pretty. So all you got to do is go zoom and then hit 7, and look, there's my graph all set up on trig. No longer is this zoom standard 10, 10, 10, 10. This is now zoom trig, set up perfectly for your questions. How beautiful is that? And lo and behold, look what we have here. An intersect here and an intersect there. How do we find them? Remember, those are x-intersects, so you go into your second calc, right? And you're going to find the zeros. All right, do the right bound, left bound thing. So let's move over here. We have to figure out the left bound first. Enter. There's the right bound. Enter, and we hit enter again. And look, I got a value of 210 degrees. Isn't that neat? So I can go back to here and say, well, this value right now is 210 degrees. Great, but you're missing something. Check this out. There's another one over there. So do exactly the same thing. Second calc. Find me that 0 and mouse over to my left bound, right bound thing all over again. There it is. Enter. Over to the right bound. Enter and enter. And I got 330. So I got 2 possible solutions for this. Now you're probably saying to yourself, well, wait a second there, sir. Sir, wait a second. Does that mean that's the only solutions? Yeah, the reason why is because look, if you look at this, zoom trig gives us basically this. From here, which we know is 0 degrees, all the way out here to about 360 degrees. So it gives you one complete revolution around the circle. But it also gives us, guess what, from 0 degrees to about minus 360 degrees. See what I mean? So it goes forward and backwards, and we can see that these guys intersect here and here, but those would be on the minus side, right? So not only are we going forward here like this and saying, oh, there's 220, there's the 300 that we're talking about here, right, the 2 degrees, but we can also go backwards and say, oh, there it is, there's the intersection there, and oh, lo and behold, there's the other intersection in the negative realm as well. So how do we turn around and say, oh, I only want these to be the positive values? We're going to get into that as well. We're going to get into the fact that not only do I want the positive values, I'm going to have to somehow restrict my domain and say, only look at this part. Oh boy, does that make things a little bit more complicated? Not really, not really. Okay, so let's keep on going then. Let's look at the algebraic method. The algebraic method, if you think about it, it is no different than solving a simple linear equation like we did here. The only difference is this now becomes, yes, it becomes a sign ratio. And remember, the sign ratio means that we're looking at the y-coordinate. So the y-coordinate is minus a half. Ah, okay. So what do we do with that then? Well, the actual answer, as we wrote here, is dependent upon whether or not you've restricted the domain. If we've restricted the domain, we would have to say, okay, in that 360 degrees, right, we already know the answers to be 210, it was out here, 210 degrees, we figured that out, and I think it's 330 or 300, something like that, I can't remember what it was. But we've already restricted the domain here by saying that we're going to make one positive revolution of the circle. But does that mean that I have to look at it from positively? No. What if I look at it from here and I say I'm going to restrict the domain from 0 to negative pi? I can do that as well. And then these values have to be figured out and calculated with a negative value in front of them. You see how it works? Okay, so what I want to do here is I want to just continue solving this. And I'm going to show you. Okay, let's look at this in terms of steps. That's the best way to do this. So we already put this equation that we had initially down into the simplest form. Now we have to start applying the trig part of the question. Okay, so first things first, we're going to determine the cast rule. All right, if you determine the cast rule, this is add sugar to coffee, just like we did before, right? We notice that sign is negative here. So think about where sign is negative. Not here, not here. Ah, sign's got to be negative here, and sign's got to be negative there, right? Okay, so we are in fact in quadrant 3 and 4. Once we've determined what quadrant we are in, we no longer need this negative sign. Because if we're doing algebra later on, that negative sign is going to mess us up something fierce. So determine where it is, figure out it's in quadrant 3 and 4, and then get rid of that negative sign. So what does that mean? Take the absolute value of this, because the negative is redundant at this point. You know it's in this quadrant and this quadrant. You don't need the negative anymore. Now, simply solve this. Solve this as a quadrant 1 kind of phenomena. And you know in quadrant 1, right, pi over, or I should say 1/2 relates to this point right here on the unit circle. The thin guys, right? That's going to be root 3 over 2 1/2, there's your sign of 1/2. And you recognize this as being, oh, that's that 30-degree mark right there, right? Or you can write it as either 30 degrees, or you can write it as pi over 6. Now that we've determined, and remember what we're determining here. You're actually determining the reference angle. Oh, fantastic. I figured out the reference angle to be pi over 6 or 30 degrees. Yippee skippy. So that's step 2. Now, apply that reference angle now to your wonderful quadrant 3 and quadrant 4. Okay? So you know in quadrant 3, it's going to be here, reference angle 30 degrees. Or it's going to be in quadrant 4, out here, reference angle 30 degrees. Now you can give me the actual angle in standard position. Starting here, going all the way over to 180 plus 30 more. 180 plus 30 more, that's 210 degrees, okay? Or you can start here and go all the way over right, to 360 and just go back 30 degrees to give you your 330 degrees. Now, how do we do this in terms of the pi over 6 stuff? Ah, okay, simple. Draw in your two rectangles that we use to determine this and just start counting. Pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6. Oh, look at that. That's 7 pi over 6. Keep on going. 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, which is this guy right here, 11 pi over 6. Or you could have went all the way around, right, to 2 pi, right? You'd have to convert that to 6. So this would be 12 pi over 6. That would make it easier. And then go back pi over 6 to give you, yeah, subtract out that pi over 6 because there's that reference angle for you, giving you 11 pi over 6. Pretty sweet, isn't it? Now, we're going to do tons more of these. But remember, here's the thing that's very, 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 very important to see here. This is based on one rotation of the unit circle. It's based on one rotation of the unit circle. So what's going to happen, I'll go back to my calculator here, I'm just going to quickly erase this. What's going to happen if we're not looking at one rotation of the unit circle? So in other words, check this out. I'm going to go to my window settings, and instead of putting 495 or 360 down, because if I put 360 down, take a look at my graph. It shows you the two intersects that we had, which were, of course, here, right, and here under a 360 rotation. There's your 210 and 330 degrees. But watch what happens when I change this window and I change it from 360 degrees to 720 degrees. Watch what happens. This is really cool. And I want to erase these little dots because I don't want them to confuse you. Watch this. So I'm now doing two rotations of the unit circle. Well, in fact, look what happens. There's the first one at 210 degrees. There's the second one, which we know is 330 degrees. But take a look at this. They show up again. But when do they show up? Think about this. This guy would show up, right, as you're going through the unit circle. And there's the 210 degrees right there. As you go once through this unit circle, it's going to show up there. But if the second you go through this unit circle, past this guy, and go a second time to that point, guess what? You have a co-terminal point. So how do we get from here to here? Well, surprisingly, for right now, we're just going to add periods of 2 pi. So if you actually add an extra 360 degrees to this, or 360 degrees, or 2 pi to this, if we were talking radians, we would get this point. Watch this. 210 degrees plus 360 degrees works out to be 570 degrees. That's one complete rotation around plus another 210 to get you to that nice little coterminal point. I'll prove it to you. Watch. Second calc. Let's find that 0. Sorry for the mess. Let's go all the way over to that point then where I was showing you earlier. Right over to here. And I'll bet. Watch this. Enter. Here we go. Enter. Bada boom. 570 degrees as predicted. Now I see. Now I see. So look at this. I'm going to take this guy here, and I'm going to do the same thing, and I'm going to predict that point. Well, you know it's going to be 330 degrees, one complete rotation around, right? Plus all the way over to 330 again. So basically, I'm going to take that 330 degrees, and I'm going to add 360 degrees to it to give me 600. Look at this, 690 degrees. I bet you this guy right here is going to be 690 degrees. Let's figure it out. Second calc, find me the 0. Here we go. Left bound. Let's go right close to it. There we go. Right bound. Enter, enter, yes. And there it is, 690 degrees as predicted. So what does that mean? Well, if I'm restricting this to 360 or to a 2 pi rotation, that's one thing. But what happens when I start expanding this? What happens when I don't restrict the domain? Well, I'm going to have to add a multiple of this. What am I talking about? Well, basically, I have to multiply this by, yep, the 2 pi. So the general solution then becomes an infinite number of solutions. So how do we indicate that we do this all the time? You're going to add up multiples of what we call the period of the sine function or the cosine function. And we're going to get into periods not so much in this unit, but in the next and subsequent podcasts. How do we go about doing and figuring out the period? Very, very simple. But basically for this one, think about it. We're going to add 360 degrees to that number. Or that number, which was 210 to begin with, adds 360 degrees. But what if I wanted to go on and on and on and on and on and on forever? Well, if I wanted to go on and on and on forever, wouldn't I have to multiply it by some factor? And that factor, of course, is going to be a positive number. And it's in fact going to be an integer. So in other words, how many revolutions is going to be determined by this value. So my answer is 210, which is out here. The number of revolutions, you're going to keep adding 360 to this number. Add 360 again. 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 And you can keep on adding 360s for an infinite number of time. That's why this k is going to be a value that's going to be the integers. Now you're probably saying, integers? That means I can go backwards. Yeah, no kidding. I can go here, and instead of going forwards, I can go backwards. The 360 degrees. Well, what about the other guy? What about this guy that was out here? I could do the same thing to him and say, oh, look at that. We had 330 degrees. I'm going to add multiples of 360 degrees as much as I want. So I'm going to go here and say, add 360 degrees. I'll get back to here. Add 360 degrees, add 360 degrees, or I can go backwards and say subtract 360 degrees, subtract 360 degrees. But the neat thing is, it's always a multiple of whatever the period is. The period being from one to the other based on the kind of graph you're doing. Okay, so what does this mean for this? Okay, what it means for this is in degrees, look what I did, right? And I added an n here. N was a matter of integers. Well, I don't really care if it's n or k's or q's or whatever you want to do. You just know that it's got to be a multiple of 360 degrees. Well, how about in radians? Then it's going to be a multiple of 2 pi radians because it's 360 degrees. So the n represents the number of rotations. Okay, either a positive rotation or a negative rotation. You don't care, right? So think about this now. We got to look at this in terms of an interval. And the interval we're looking at is either a negative pi over 2 to pi over 2. We're looking at, are we talking about including one rotation positive and one rotation negative? Well, if we do, remember, this is an equal sign, hard bracket, negative 2 pi, equal sign, hard bracket, 2 pi, right? Kind of interesting. Or are we restricting this domain to, let's say, something that looks like this? Then we'll have to go hard bracket here, of course, because we're including the 0, soft bracket to pi. It all depends on the question and how they're going to restrict the domain. Lots of info for an intro, hey?